Belduis. Professor Belduis is from Twente University. But he has a lot of industrial experience. He worked for some years at Philips Research, correct?
Yep.
And then he moved to the Institute of Perception Research in Eindhoven, where you were working on speech processing.
Yeah, correct.
And now Raymond is full professor in biometric pattern recognition at the University of Twente in Netherlands. And you were mentioning that now you are also leading the group on
data science.
Data science, Emanuele. Data science. So good. So he works on many different research topics. Among them, there is face recognition, 2D and 3D face recognition, fingerprint recognition, vascular recognition, so vein patterns, and biometric template production. So I would really like to thank Raymond for taking the time to come here and giving today's seminar, and also he will give another seminar on Friday, and it will be on biometrics and the forensics. And let me also say that this seminar is within a series of seminars organized by the IEEE Italy section biometric chapter. Okay, so Raymond, please, the floor is yours.
Thank you, Patricio, for your introduction and for inviting me here. It's a real pleasure being here. So, Patricio already reviewed my CV a little bit. I'll skip that part. What I will tell about biometrics today is not so much about face or fingerprint recognition. It's more about how we can make optimal use or good use of the discriminating properties of biometric features. So at the very end of the biometric process, what we will do is we'll extract some features and we will be comparing features, and I'll be talking about how to do that in the best possible way for certain feature types. The talk has two parts. The first part will be about likelihood ratio classifiers for histogram features, and the second part will be in the domain of biometric template protection. So biometric template protection is about storing biometric data in such a way that it is securely stored so that no one can get access to the biometric template. And both parts will be about hopefully 30 minutes, a little bit less. If you have questions, I don't mind being interrupted, so if there's anything that is unclear, please ask and I'll try to clarify. So first part, this is work actually done at a stay at the NTNU, Norwegian Technical University, the department in Gjøvik, together with Kiran Raja. And the problem, and it's about classifiers for histograms, but let's first start at looking at classifiers as such. What question does a biometric classifier actually answer? Well, we see that on the right-hand side over here. This is a biometric application. Basically, it's face recognition at an airport, and what we have is there's a facial image stored in the passport, and there's a live scan of the lady over there, and the question that the system wants to answer is, are those images from the same person? Because if the answer is yes, then she must be the rightful holder of the passport and she can actually cross the border. The type of classifiers that we're looking at in this example are histogram classifiers. You can also use them outside the biometric case, for instance, by comparing documents. For instance, you can make a histogram of all letters that appear in the document, and then you would be able to compare documents. And then the question that the classifier would have to answer could be, are these documents about the same topic? Assuming that if we would do word counts, for instance, that those histograms of typical terms would be the same if these documents are about the same topic. So both questions are actually the same. The next thing is that if we want to design a classifier, and if the question is, are these features from the same source, what would be the best classifier? And the answer comes from statistics. You're all doing electrical engineering, right? So did you do anything on communication theory? So you learned about detection theory as well, maybe? So did you learn about the optimality of likelihood ratio classifiers? Maybe, maybe not?
Yes.
Yeah, okay.
Yeah, sure.
Yes.
Yes. The answer should be yes.
Okay. You're told that you have learned about this. Right. So the likelihood ratio classifier was actually developed in radar technology, I believe. And what it does, it's optimal in decision making in the sense that it optimizes errors. So if you look at the characteristic on the right hand side, this is, so you know what a receiver operating characteristic must be. And we have two types of errors in biometrics. If we use ISO standards, we talk about a false match rate, also known as false accept rate. And the other one would be a genuine or true match rate. So if you know these things, then the likelihood ratio classifier has the property that if I fixed any false match rate, then it will give us the maximum true match rate. So it will give us the best ROC. And that is interesting because that will probably be the best classifier. Now, in our case, what does a likelihood ratio look like? Basically, it's a ratio of two probability density functions. The probability density function under one hypothesis divided by the probability density function under another hypothesis. And our hypothesis here is, first, both samples, X and Y, are from the same person, divided by the probability density function that X and Y are from different persons. What is a bit different with the detection theory is that we have both samples here as argument in the probability density function. But this is because in advance, we don't know who X and Y are. So we have to know the probability density function. And in general, we don't know. So we have to measure or we have to estimate. For instance, we could assume Gaussian probability density functions in the next. Now, before I go into that, I would like to say something about what is so nice about the likelihood ratio. Why is it optimal? Can I explain that? And here you see a historic, almost robbery of an ATM machine in Norway. It was after a dinner with my colleague Christoph Busch that we decided to rob an ATM. And Christoph Busch would take the pictures. So this is my colleague Erwin, who happens to be over 2 meters tall, robbing the ATM. And after he did that, I did it again. And I'm a little bit smaller. Actually, I'm not 176 or 175, I'm 186, but for the example, this is a bit better. So what we have here is two cases, let's say two forensic cases. And let's assume that there is a surveillance camera somewhere, and because we have a nice geometrical structure over here, what we can do actually is using this structure to get an estimate of the height of the robber. Now, let's consider two cases. So case one, we have a trace. Trace is the measured height. Let's say 1.75 meters. Now, this case was reported to the police. The police went around, they picked up a suspect. The suspect has a height of 1.76 meters. So this is all the information that they actually have. This is case one. And the difference between heights is 1 centimeter. Now there's case two. There's a trace saying, hey, the robber must be 2 meters tall, which is pretty tall, especially in Italy. In Norway, it's not that tall, but in Italy, it's pretty tall. And we have a suspect, and the measurement was 2 meters and 1 centimeter. And it could, of course, be that these measurements are not completely accurate. Now, my question to you, which case makes more sense? The difference in both cases is 1 centimeter. If you were the police, which suspect, would this be a likely case or would this be a likely case? Who would vote for this one? Who would vote for this one? Okay. Actually, this is the most likely case. So if this is the case, then the probability, the likelihood that the suspect actually robbed the bank is much greater than in this case. If you would just measure differences in height, both would be 1 centimeter. But people of 2 meters are pretty rare. So if you find a suspect that is close, then probably it's much more likely that this suspect actually robbed the bank than in this case, because if the trace is 175 and there are a million people of 175 or 76, it's not very likely that this person did this. So if I compute likelihood ratios, then actually here I find 4, which in a forensic case would actually not make a lot of sense. People would say, okay, this is not strong evidence, but here I get something like 1170, which is a much higher likelihood ratio. So the likelihood ratio in this case is much higher, and that confirms our intuition that actually this is a much better case than this one, if you want to convict the subject. So that's what it does. And we would say it rewards rareness, where a classifier based on just measuring differences, like a Euclidean distance or a Manhattan distance or even a cosine classifier, only rewards differences. This one also rewards rareness. So that is what makes it interesting. Okay, one piece of equation. This is the original definition of the likelihood ratio, and if we work this out, we know that when x and y are from different people, they're actually statistically independent. So the equation simplifies like this. Now let's go back to our features. I would like to talk about histogram features, because histogram features play a role in biometrics. For instance, we have local binary patterns. I don't know whether you already have heard of them, but what they do is they measure certain patterns in human skin, and they basically per pixel they produce a number, could be an 8-bit number, and that number is put into a histogram. And then if you want to compare two faces, what you want to do is you compare two histograms. Another feature, the BSIF also produces histograms, so you want to compare histograms. Histograms of oriented gradients is another way where you measure occurrences of angles in data. All these texture classifiers produce histograms, and basically the comparison is made by comparing histograms. In text, the histograms could be unigrams or n-grams, measuring the occurrences of words. Okay, so we want to compare histograms, and normally what is used in biometrics to compare those histograms is the chi-square distance, which is the standard comparator. Chi-square distance is an equation where you put in the two histograms and you get a number. It's a distance metric. But we could assume, actually, that if we have a histogram, that can be seen as a multinomial probability distribution. There's a probability that every bin of the histogram will get a hit, so every bin will have its own probability p of I, which we don't know. And then the probability, so this is a parameter p, the probability is the multinomial distribution on x given the probabilities of the bins. So under certain assumptions, we could assume that a histogram can be modeled as a multinomial probability distribution. So then we have x with a multinomial and y with a multinomial, and if these histograms are from the same individual, then they must share the probability. If they're from different individuals, then they most likely will have different probabilities. Let's say P from the same and P and Q from different individuals. Now, if we have probability distributions, we can set up a likelihood ratio. So let's try to do that. And there's a little problem here, because we don't know P. We only know that if they're from the same individual, then they must share P, and if they are from different individuals, then they will have different P and Q. So what can we do about that? Well, actually, we can infer another probability distribution on P. Say P is also drawn from a probability density. And there's a probability density that comes very natural with the multinomial, which is the Dirichlet probability distribution. The equation is a bit too complicated to write up, but it's a probability distribution on the probability vector P, and it has parameters alpha. So that is the next thing, and this actually explains the problem. Suppose we have the underlying probability alpha, then from alpha we draw P, which is the probability of a person. So alpha determines who you are, the person. And if we have the case where we have the same probabilities, we get X and Y from the same P. If we have different probabilities, let's say Q and R, we get U and V from different people. Okay, so and we call this the background model. Now, how can we, if we know this, we can start to write up equations. And this is the longest equation that you will see. But this one is the probability that X and Y come from the same individual. What we have is the probability that X is derived from parameters P, Y is derived from P, and this is the probability of P given the unknown parameter alpha. So if they come from the same person, they must share P, and P was generated from alpha. If they come from different individuals, you see these two integrals over here. So then X comes from P, and P is generated from alpha, but Y comes from Q, and Q is generated from alpha. So the equation still makes sense. Now, the next thing we will have to do is we have to find alpha. But first let's look at the Dirichlet distribution. This is this thing. You may not get happy when you see this, but what we see here is P2 powers. So this is how the alpha relates to P, and this is just normalization constant. This is a gamma function, and this is a product of gamma functions. We'll give names to that function, and then it starts to look simple, because this now is the beta function. You'll find this in elementary books on statistics, and there's no reason to learn these things by heart. But anyway, for instance, a program like MATLAB can easily compute those things. So this is the Dirichlet distribution, which you will find over here, and over here. And the multinomial was on the previous slide. So this is all fine. And the only thing is that we don't have alpha. So let's first see how we get to the likelihood ratio. So this is my symbol for the likelihood ratio. This is the original equation. Now, it takes a lot of effort, but I can rewrite this into beta functions. And recall, this thing is my beta function. So I can rewrite the entire equation into beta functions. And the nice thing is that they contain all kinds of multiplications, BAC multiplication. The gamma function actually looks like a factorial operator, but it's generalized in that it doesn't need integers alone. So this is like a factorial, and this is a product of factorials. But because they are factorials, they're multiplications. If I would go to a log domain, they become additions, and actually this can be calculated quite efficiently. So it looks horrible, but calculations are actually easy. So, efficient computation, there's one remaining problem. We don't know alpha. So, this parameter that drives all my probability density functions, we don't know. But we can actually collect a lot of data. So, if you're willing to train the classifier, what we can do is we can start to collect a lot of data, and we can actually find a principle to estimate alpha from data. So we have a training set, all kinds of histograms, realistic histograms related to a problem. From these histograms, we start to estimate alpha, and then from a test set, we apply alpha in a likelihood ratio. So it's basically what we always do in biometrics. We train a classifier to extract parameters, and in this case, this is alpha, and at a later stage, we use them. Well, you may have heard about maximum likelihood estimators. If you want to estimate parameters of a distribution, you may have heard this for the normal distribution, for instance, to estimate expectation and variance. Well, we can do something similar if we want to estimate the parameters of a Dirichlet distribution, and basically this is simply the thing that we maximize if we do maximum likelihood estimation. So I'm not really interested in telling you much about the details. Looks like a complicated thing, but alpha is not a very big vector. Usually we have something like maybe 100, 200 elements in a histogram, and there's a very nice optimization method which is called the Nelder-Mead simplex optimization. Has anyone ever heard of this? It's an optimization technique where you take 3 points in a space. Well, let's assume a two-dimensional case. This is high-dimensional. You take 3 points in a space, and then these 3 points and the minimum point, they form a triangle. So if you want to climb a hill in a two-dimensional space, 3 points form a triangle, and you look at the lowermost point. You want to go up. So what you do is you flip the lowermost point with respect to the line by the other two, and then you get a higher point. And then if you repeat that, you'll find that you'll be slowly climbing a hill. This is what you can do in 2 dimensions, but you can also do that in maybe 100 dimensions. So this is Nelder-Mead. The nice thing is it requires a minimum of evaluations. It converges pretty rapidly. So this is what we developed in order to estimate the alpha. Okay. Now, just to show that this works, this is an illustration of the estimation process. What I did is, this is a histogram, and these circles are the original alpha parameters. So what I did is I chose alpha parameters. Actually, I chose them in a simple way, increasing from 1 to 50 linearly. You don't have to do that, but this is just for the example. So I generated histograms with these given alpha parameters. From the alphas I withdraw p's, for the p's I got data, and from the data I started to estimate the alphas again. Then, as an initial estimate, we simply took average probabilities, and then we take a final estimate, and we had an iterative method, and we see that what we found was basically the triangles. They're almost close to the initial estimate, which is pretty good. But from the data, we're not very far off the original underlying estimate. So we were happy enough to use this. And then, so what we have now is a likelihood ratio equation. The likelihood ratio equation depends on the parameter alpha, and we have a method to estimate alpha from the data. So we can almost start using this. With a biometrics background, have you ever heard about feature selection? Who has? Okay, so if you have a lot of features, then in some cases, if I have too many features, my classifier work well on a training set, but it will not work well on real data, because I kind of overtrained the classifier. So it could be very useful to reduce the number of features, and generally it's nice to play around with the number of features to come to some kind of optimum. This is also true in this case. So if we have a histogram of, let's say, the common histogram for LBP or for BSIF is 256 bins. And the question is, are all those bins equally useful? So we started to develop a feature selection method, and you basically, the way you do that is you develop the full classifier with a number of features, you measure on a validation set the performance, and then you start to reduce the number of features in some way, and you see whether your performance increases on the validation set. We also did that. Point is, for this case, we don't know what are the relevant features. Are those the features, let's say, with low probability, or high bin probabilities? And we started off by thinking that low probabilities would be less relevant. It didn't work. And then, just by trial and error, and this is one of the open ends of this research, we started to reduce by removing the bins with higher probabilities, and that actually works. And we still don't know why. So this is going to be presented at BITAS, and it's not completed research, it's still an open end. There are some questions that we're left with. What we see here is the number of bins going up. Well, I started at 60 to 256. This is a real case. This is periocular recognition. So what we want to do is recognize a person by the data contained in this little area around the eyes. And for that, BSIF features we used. And we played around with the number of features, and what we measured here was a true match rate as a false match rate of 0.1%, which is just a performance indicator. And then we see that if we we see the results of two classifiers. This is the developed likelihood ratio classifier, and we see that if we increase the number of features up to a certain point, here it reaches a maximum, and then it goes down again. If we look at the competing classifier, which would be the chi-square classifier, the advantage is that it's untrained. We see that it continues to increase, but stays below the likelihood ratio classifier all the time. So feature extraction actually makes sense. It's also pretty robust because whether I start here or here does not really matter a lot. So that was theory developing the system. Then we did some experiments, and these are the results for the left periocular region. Data was generated by Kiran Raja from NTNU. We had 100 subjects for training, not a very big data set, 46 for testing. We used BSIF features, and we had for training we had 15 histograms per subject available. And we had a number of bins of 256 reduced to 175, which was optimal, as you could see in the previous slide. We did one-to-one comparison. So this is a likelihood ratio classifier as I developed with an estimated parameter alpha from the data. And this is the chi-square classifier that is generally used for this kind of application. What I didn't tell you is that I can also derive a user-specific likelihood ratio classifier, where I just for one user estimate this probability vector, and then I can develop a likelihood ratio classifier in the same way. It's a little bit more simple equation. The problem is that for every user I need the data to estimate the classifier. And I can have a multi-enrollment variation where I do not compare a sample to one other sample, but I could compare it to, let's say, 5 or 6 other samples. And there's basically this classifier is identical, but I simply add up the histograms. And I'm comparing this to a user-specific chi-square distance. So there is a one-to-one comparison, two unknown feature sets being compared, or a user-specific one where I compare for specific users. And I'm putting this iPhone image here because basically what the iPhone does, it trains a model for every user. So this is a very convenient situation for biometrics because you can collect much more data and you can tweak a classifier to one user. And this is what we're actually doing here. So let's look at the results. These are ROCs again, false match rate over here, ranging from 10 minus 4, so 0.01% to 100%. And these are true match rates, and we see a number of lines. The blue ones are the single enrollment case, or the one-to-one comparisons. So unknown, comparing unknown people. And we see that this one is the likelihood ratio classifier, and this one is the chi-square classifier. And we see that in the ranges of interest, actually, we have quite a performance gain. For instance, by, at this point, 10 minus 3, so 0.1%, we go from 94 to 95% to a match rate. If we look at the user-specific cases, we get better performances, which is to be expected, because we can train to a specific user. And here we see that this is the chi-square, and these are the two versions, the multiple enrollment or the subject specific, and they actually are basically on top of each other. But again, here we see quite a substantial performance improvement. So, at the end of the first part of my talk, what did we do? We developed a, well, I gave a nice introduction, little introduction about why likelihood ratios are nice. And we developed a likelihood ratio for a very specific kind of features, which are histogram features, often used in local binary patterns. We developed maximum likelihood estimation for the background model. We did two kinds of comparisons, one-to-one and user-specific, and we, of course, the user-specific one actually outperforms the one-to-one. They all outperform the commonly used chi-square classifiers. We're now testing on other data sets because this was just a preliminary instrument, and we concluded that feature selection is beneficial, but actually it needs further research to understand why it happens. I'll move on now to the next part of my presentation. If you have any questions about this, this might be the moment, and otherwise I'll move on.
Yes.
Okay. So, there's a whole lot of people over here, and they all contributed in some way to this work. And actually, there are even 2 people in this audience who also contributed to this work, but they probably don't know yet. They'll see this a little later. It's about homomorphic encryption. Who knows what homomorphic encryption is? There's 2, 3. Okay. That's a challenge. Who knows what biometric template protection is? There's more. Okay. Let's see. That'll be explained in the introduction. So this is a review of my paper. Results are published. We're working on the better paper, but it's on archive at the moment. It's work done mostly by a student and by some of you actually. This is a kind of scheme for biometric template protection. I'll just leave it as is, but I'll tell a little bit of the idea is that biometric information, let's say images of faces or fingerprints or irises, are actually sensitive information. If you can steal them from someone, you can impersonate those persons if you want, or you can maybe extract medical information. So there is a desire to protect biometric data. And protection actually means that you cannot go back from the biometric data that is stored to the original underlying biometric sample. So whatever I store from a fingerprint should be stored in such a way that from that information I cannot retrieve my fingerprint. That is the idea. And there are 2 principles now being considered for that. One is biometric template protection in helper data systems, and the other one is biometric template protection under homomorphic encryption. And they're kind of in competition. There's the one category has certain advantages, and the other category has other advantages. And performance-wise, one is probably better than the other. But that doesn't always mean that it's the preferred solution. So, what happens in the standard way of biometric template protection, the helper data-like systems, is that I have biometric data. I mix that somehow with a key that I secret key that I generate. I can store the key somewhere after hashing it in Vault, and I get 2 types of data. One is the biometric data, and there's helper data. And both of them are actually uncorrelated and do not relate again to the original biometric data. I can do the same thing at verification moment. I take the biometric data, I take the helper data, I mix the 2, and what I get back is a version of the key that I stored, and then I can compare. It's a very simple way of putting it. The drawback, this is an elegant system. It has been implemented and it has been investigated for many types of biometrics. It has been known under different names, and they all lead back to the same principle, mixing the biometric data with a secret, a binary secret in some way, constructing helper data, then on verification we use the new biometric data and the helper data to unmix. We extract the secret and we can compare the secret to something that has been stored in the vault, and the nice thing is we can do that under hashing. That is important because if I would just hash the biometric data, it wouldn't work, because no biometric sample is the same. But if I do it in this way, I can build in some error correction possibilities, and then I can actually compare the extracted secret. The drawback of this principle is that the protection is as good as the biometrics. And if I would estimate, and I did that in a paper presented at ICP 2015, if I would estimate the secrecy of the biometrics, if I would express that in bits, then for a good fingerprint recognition system, for one single fingerprint, I would come to maybe something like 15 to 20 bits. For face, it would be below 10 bits. That means that, and if I would tell this to cryptographic experts, I would be laughed away. A secret of, let's say, 10 bits is useless. A secret of 15 bits is also useless. So in fingerprint recognition, what we could do actually, and this is happening, we can take 10 fingers, and then these bits kind of add up, and we have many more bits. But in general, the disadvantage of this type of system is that their secrecy is directly coupled to the biometric performance. If I decouple that, what I do is homomorphic encryption, or is encryption. But the problem with encryption is that if I encrypt my data, normally I would have to decrypt before I can compare. If I use homomorphic encryption, what I can do is I can implement certain simple operations under encryption. So I can do some calculation under encryption, and I can try to do my fingerprint or biometric comparison under encryption. And people here have been working on that, maybe are still working on that, I don't know. So, the disadvantage is a much more complicated system. The disadvantage is that I would have to do key management. The big advantage is that I can decouple my biometric performance from my encryption because I can take any key length that I like. So, this is the basic principle of homomorphic encryption. If I want to do a certain operation under encryption, so the double quotes parentheses mean encryption, then that actually corresponds to another operation that I can do on the encrypted data. So this could, for instance, be a multiplication, and this could be an addition, or vice versa. Usually systems have either multiplication or addition, and that is called somewhat homomorphic encryption. If you want to do everything, you have full homomorphic encryption. But, so for instance, we can do multiplication and addition. The problem is that that is very, very complex. So, need a lot of resources and computational time and communication between client and servers to do that. Another thing is all operations have to take place in all cases on integers, because this is directly related to discrete mathematics, and discrete mathematics, well, they could be mapped onto integers, but not onto real numbers. So, in overview, if I look at the PI framework, so the standard way of biometric template protection, there's no key management, it's computational simple. There could be possible loss of recognition performance, because at a certain point I have to go from my biometric data to a binary vector. But the most important thing is the low security or privacy protection, because it's determined by the biometrics. And the theory about that is in this paper. Homomorphic encryption, well, you need to do something with a key. Keys are involved. It is computationally complex, because it has protocols that require communication. There could still be possible loss of recognition performance, because as I told you, we can only do simple things. So usually what people implement as homomorphic classifiers are very simple classifiers, like Euclidean distance or inner products. And there is a high security privacy protection, because it's just determined by the key. So there are pros and cons to both. What we will do here, and therefore it's nice that the two topics that I discuss are compressed in one seminar, is I want to do biometric comparison on the homomorphic encryption that is actually virtually without loss of recognition performance. And it's computationally simple. And that is because we're going to implement a likelihood ratio classifier, which is optimal. But it's also very complex, so there are a few tricks involved in order to implement this in the homomorphic domain. So, without loss of performance, computation is simple. We have a client-server architecture that does that. The requirements are that both client and server do not learn about the template that is stored, so fully secret. The server does not learn about the probe, so the server is the database where everything is stored, does not learn anything about the biometric sample that is produced. Client and server do not learn about the comparison score. If you remember the diagram at the beginning, when we do biometric comparison, we produce a score, we compare the score to a threshold. We want to keep the score secret, because if we reveal the score, in many cases we have homomorphic encryption with a public score, you can still do hill climbing attacks, and the server does not learn about the decision. So only the client, the guy that puts the fingerprint on the sensor, learns about whether he's accepted or not. So the database doesn't learn anything. So let's move on to this. This is the architecture that we're looking at. So there's a reference. It's not a fingerprint actually, but this is the image that I use. There is the standard normalization that we have in biometric recognition. There's feature extraction. Here's my feature X. There's there's encryption, and this is where we store the data on a server. Could be one sample, could be many samples, could be one user, could be many users. At verification time, there's the same procedure. There's feature extraction. The feature is not encrypted actually, it goes directly into the client. This saves time and it does not affect the secrecy. Then we have a comparator that can compare an encrypted feature over here with an unencrypted one over here. It gives us a encrypted score, and the encrypted score is in the encrypted domain compared with a threshold, which you do not see very often in homomorphic encryption. And then there's decryption, and there's a decision match or non-match over here. So this is the system that I would like to discuss. Well, again, a bit mathematics, but most of these things I explained. My score is actually a log likelihood ratio. And this equation, you've seen this equation, you've seen. Now, I want to manipulate my data in such a way that x and y are vectors. So they contain many features. I want to manipulate my data in such a way that these features become statistically independent. If I do that, then the probability density functions multiply, and this simplifies to this. And I include a log over here. So I get a sum of logs. So what I want to compute is a sum of scores. And the theta i's are just parameters over here. So what I want to do is I want to focus on a smart, and this is a summation I can do under homomorphic encryption. So what I want to focus on is a smart computation of this one. Because if I can do that in a smart way, then I can actually simply do my summation, and there's still the question of the comparison with the threshold, which is not trivial. Now, I assume that my data has a Gaussian distribution. This may look like a strong assumption, but I'll show you two examples afterwards where you can see that actually this works. So I'm assuming that my data is Gaussian, has a Gaussian distribution. So this is the probability, the blue line is the probability density function of a single feature. And I have many of these features, and what I can do by normalization operation is I can centralize them around 0, and I can give them unit variance. So this is just an operation. Then you see feature X over here, feature Y over here, and this is a height map. Ignore the grid. This is a height map of my score function, my likelihood ratio. What we see is it's dark here, so if X and Y are different, likelihood ratio is low. It is kind of bright in the center, and we see that at the edges it's actually even brighter. The reason for that is that this likelihood ratio rewards rareness. So if I have two rare features, then I get a higher likelihood ratio than when I'm in the center. What I will do in the next step is I will quantize these features. Now quantize them in equi-probable intervals. So this is a 6-bit case, and every interval has the same probability. That makes life easier if I just want to avoid guessing. So this is the score, and the score is a likelihood ratio. And then I could quantize my likelihood ratio. So instead of using the real numbers, I discretize it. X could be an interval y of k, y could be an interval y of L. I just denote the intervals. And then my new likelihood ratio is the log of the probability that x is in interval k, y is in interval L, under the assumption that they're the same, or the independent cases over here. And that will give me a value, again a real value, and because I want to do homomorphic encryption, I would still also have to quantize that value in some way. So this is the thing that I actually want to compute. So this is my quantized LLR, QLLR. And the parameter here is the quantization step size over here, and another parameter is how many intervals I use in this case. So this is x quantized, this is a 3-bit case. I get 8 intervals, and I see that my likelihood ratio image, so the one that I showed here, this one now goes to this. Trick that I do here is as follows. If I want to make a measurement at enrollment, I get a feature. I quantize that feature and I determine in which column the feature is. Column, let's say this column, 2 over here. I encrypt and store the entire column. Then, at verification, I simply quantize, and if I encrypt and store it, I don't know where it originally is from. So secrecy complete. At verification, I figure out where, in which interval my sample is, and I simply pick in this stored column, I pick this value, which is fully encrypted, so I don't know what's going on, and I add that to my score under encryption. So this is again displayed. Now it's quantized in, I think, 64 levels. And this is a 64 bits, 6 bits, quantized with a step size. And here, just to illustrate that this only gives a very marginal loss of performance, the red line is the original ROC for one single feature, and the dashed line is the ROC after all the quantization steps, if I do it like this. So I hardly use performance. So, procedure. At enrollment, measure feature element X. I encrypt and store all elements in this column. So whatever Y is, these are the possible outcomes at verification time. And I store this encrypted value. Then I thresh Xi, so I discard my input sample and leave in the value K. The only thing that I have left for this feature is the encrypted values in that column. Then, at comparison time, I measure my feature. My feature will give me a pointer to this element, for instance, which has been encrypted, and I update my score. If I start with score 0, and I simply add under encryption my score. So, and I can do that for all the samples, so I can compute my complete score. Now, scores are computed as integers, so I need to round them. I still have to compare with a threshold. And that's a bit delicate because I only used additions so far. Comparison with a threshold under encryption is very hard. But I do not want to reveal my score, and this is the most time-consuming part. But we are working with integers. So, if I would take my score, and if my score would be larger than the threshold, then if I would take the threshold and I would subtract the score, this value would be below 0. I also know in my calculations I have a maximum score, and the maximum score is certainly higher than the current score, so this value would be above 0. So if I would compute all these numbers, then if my score would be above threshold, this sequence would contain a value 0. If my threshold is below if my score is below threshold, then this would be a positive number, and this would also be a positive number. So there would be no 0 inside my sequence. So this is a trick to compare with threshold. Well, let's see. And this is how this is implemented in in the encrypted domain, because I have to subtract, and subtraction, if addition is a multiplication, subtraction is division, I can easily do that. It's not enough. I still have to randomize this sequence. I can do that by multiplicative blinding and just taking a random value, taking it to the power of something. And then if it's 0, then it will still be 0. So the 0 will remain, but these numbers will become meaningless, and I can also randomly permute them. So order effects are also gone. And then after the description, the only information that is valid is whether there is a 0 or not. How did we solve this? Well, we used Al-Gamal encryption because my cryptographic colleague said that this would be the ideal thing to use here. It's probabilistic encryption, so that means that if you encrypt a number once and you encrypt the same number twice, you get totally different encryptions. The key is a shared key. There's a client part to the key and there's a server part to the key, so both can encrypt and decrypt, but you need both keys in order to be able to do full decryption. And in this case, we assume trusted enrollment. So the first part, where we store the biometric data, has to be a trusted environment. Now, this is the second time in my life that I present the cryptographic protocol, because I'm not from cryptographics, but at the client. So suppose at the server we have the biometric data stored, the enrolled data stored. At the client, we have a biometric sample and the ID of the client. The ID is needed to retrieve the correct information. So the ID gets to the server, and the server will give us back the row in the matrix of encrypted scores. Then, this is the addition process where the client actually produces indices in these tables. This is where they are encrypted, and then the encrypted score goes back to the server. The server then subtracts the score from threshold up to maximum score. So this is the sequence that must contain a 0, decrypts it partially, sends it back. Client can do full encryption and can test whether there's a 0 or not. So let's show some results, because this is theory we have implemented. We use two types of data, and this is where you guys come in, at least two of you. I asked Marta. Almost everyone in the world knows Marta.
Absolutely.
No need for further explanation. I told her about this and I said I need some, and I knew that she had been working on homomorphic encryption in biometrics, so I said, okay, what I need is some data to prove that we actually have a very good system. And she said, well, you can have the data that we used, and I have results that we used, that I used in Italy here on signature data. So this is what Marta did. And I use the same data in a slightly different way, and I want to compare the systems. So, the data is dynamic signature verification data. The features that I use are the 40 features that Marta extracted from this data. The same 40 features, I don't even know how she extracted them. The same 40 features that she used, I use. She used a system with 5 enrollment samples, so per comparison she compared to 5 people. To 5 samples of 1 person. I just use 1 enrollment sample, which is a harder case. She used a Euclidean distance or a cosine classifier, either of the two, for 40 features implemented under homomorphic encryption. I used the quantized likelihood ratio classifier with 8 bits per feature and a step size of the quantization step size of 1. Same features, but before that I applied some PCA-LDA transformation. She had a public score, we have a hidden score. Subject in training, well, the advantage of this is no training examples needed. We used subjects that were not used in this comparison, so for training. Subject in testing, same sets. Well, if you look at the number of scores, then there were 4,000 genuine and 8,000 imposter scores. We could go to many more scores because we don't compare to 5, but just to 1 person, so these numbers are higher, which probably means that our measurement of the ROC is somewhat more accurate, but that doesn't really matter much. She involved forgery testing because that is relevant for signature. We didn't do that. We just wanted to know whether the standard recognition performance was better or not. So, this is the scheme. These are signatures, by the way. There's feature extraction, and we added PCA and LDA in order to make the features more or less independent and to get them into the right framework. And this is the system that I just explained. And here we see the results. These are from the paper by Marta, Emanuele, and Patrizio, and maybe some other people present in this room that I don't know yet. What you have to look at is these are the scores, because the other ones are the forgeries. So we look at the forgeries, and what we see here is equal error rates after protection 4.89. With or without protection 4.89. With the Euclidean distance with cosine 5.5%. But this is comparing to 5 individuals, to 5 samples. This is us. This is unprotected, this is protected. We see protected is actually even slightly better, because sometimes quantization helps to make it more robust, the slight differences. And we get to equal error rates of 2.7 or 2.6%. So about a factor of 2 better in a much harder comparison case. And these are Marta's results over here. So this works. And we have near optimal results. Actually, if you look at computational effort, similar. 99.4% of our effort is in comparison to the threshold. So if you skip that, if you want to have a system with a public score, and sometimes this is useful, we're about 200 times more efficient. One other example, it's about closing time, because this was signature, and with traditional features, and usually nowadays if I submit a paper, the reviewers say, why don't you use deep learning? So I've seen papers rejected because I use deep learning. I've also seen papers rejected because I don't use deep learning. I don't know what is right, but we try to do a deep learning example as well on face. This is again done in Norway together with Kiran and Raghu. And what we did is we used a standard pre-trained neural network for face recognition, VGG face. That gives 2048 features, which is way too much. And we added PCA and LDA after that in the classifier, just to get back to the distributions that we wanted. So this is VGG face. I have no comparison, but what I can do is we run this on the original FIGC experiment 1 protocol. And this is a standard protocol. And the only thing I can show here is that, hey, wow, where is my graph? This is it. Future, order, wrong order. These are the results. ROCs again. Bit of a different scale because they were generated in Norway. So this is a false match rate in percent. This line, the blue one, is after encryption. Again, a little bit lower than the red one, which is before encryption. So same technology, but no homomorphic encryption, no quantization. So again, the quantization here is kind of helpful. And what we see is equal error rates of 0.2 or around 0.2%, which is also in this FIGC experiment 1 competition, which is from long ago, but this is highly competitive. So we see that also in combination with deep learning, this stuff works. Well, takeaways. What? QLLR, integration of the optimal likelihood ratio classifier. So first part of the talk, likelihood ratio classifier is optimal. Second part of the talk, actually we can integrate it with homomorphic encryption. Actually this is a generic thing. We showed that it works for feature extraction from signature data. We had it working on synthetic data. Now we're also having it working on face data. There's a company in the Netherlands, Genki, who is now applying this on fingerprint data, and they also claim good results. So this is really working very well. We include comparison with the threshold under encryption, which is not often done, still good works, and we have, I would say, excellent recognition performance. End of the talk.
Thanks a lot, Raven, for the talk. I guess there is also material for us to study. I don't know if there are any questions from the students, from the audience. I guess we got some material to study. I guess they will be ready to understand at least the second part by the end of January.
Yeah.
So
Okay. Well, there's a paper that can, if you have copies of the slide, there's a paper that can be downloaded which tells the whole story.
okay, so do we have any other kind of more technical question? Yeah.
Yes. What's the security of the scheme when the key is compromised? The
When-
private key.
Okay, yeah. When the key is compromised, you're done. What I didn't the example here was a 256-bit key. 256-bit key. There's one other assumption here, and this is that we have what is called honest but curious systems. So the system wants to learn the data, but is not really intervening in the code. We're now working on how to get some additional protection.
And does the system need the features to be dependent for security reasons? Or because I saw that you put PCA now to uncorrelate features. But is that for security reasons?
No,
or
no,
just
that is actually only because then the likelihood ratio works optimally. So there are not many ways of computing a likelihood ratio. We had one for histograms. The other known one is actually for Gaussian data. The way to get Gaussian data is by more or less, because this is still an approximation, is by using PCA and LDA. And then you have almost a normal distribution. Independency is needed because then you can simply add the scores. If they're not independent, then the likelihood ratio of the total is not the product of the likelihood ratio. So we need some kind of independency, and we need the Gaussian distribution. There are some simplifications, some ways to get around, but this is the easiest story.
But you mentioned that the Gaussian assumption is not so strong.
It is well. It is, yeah. If I redo the experiment with real Gaussian data, I get much better results. So it means that at this point we assume that it's Gaussian. In reality, the data is not fully Gaussian, but it works good enough.
Just a question. These systems are working verification modality.
Yeah.
How do you perform an LDA?
It's this type of LDA is also known as joint Bayesian optimization. So the LDA is totally tuned towards comparing two samples, whether they're from the same individual or not.
But do you need the whole database to compute the projections or not?
You need a training database with separate individuals in order to compute the, yeah.
So with all the individuals upon which to perform verification?
No,
different.
totally, no, yeah, we never do that.
Okay.
We always have the individuals in the training set are always completely different from the individuals in test set.
No, because I don't know this kind of LDA typically, because the LDA I know
If you would look,
same users.
yeah, if you would Google for joint Bayesian classifiers, then this is where you find them.
Other questions? A kind of philosophical question about the future of template protection. Now we also have a standard of template protection.
Yeah. The picture I showed you was the ISO standard.
Yeah.
Christoph Busch has been in my audience.
Christoph Busch is always among us.
Yeah.
So, I know that. No, I mean, and also you mentioned that JK is also implementing this, which is quite interesting to me, because not many companies are really willing to spend the effort and time in implementing template production for biometrics. I don't know, because now GDPR is in place, that there is more sensitivity around this issue, or I don't know, or just because Tom is a friend. Or
Tom is also a friend, but Genki started to do this way before the GDPR. Their first product was, and actually, so they use the traditional type of template protection. Now they're also interested in the homomorphic encryption part. We have a project together to further develop this. But they started off with the standard helper data systems, which was partially invented by Philips before Genki split off. They claim that it is secure, but they also realize that security of these systems is not very big. It's also very convenient because you have a binary feature vector. So their first products, they simply had this binary feature vector printed as a QR code on a paper card. And they use this in Africa to register people for elections. It's very simply to print this paper card. You have a binary thing, has a bit of template protection, and you can compare it to a database. But this is how they use it. And they solve the security issue by using 10 prints.
10 prints.
Yeah.
I see. And you mentioned that the security bit you can get with fingerprint is around 10, you mentioned.
Per finger.
Per finger, yes.
Between 10 and 20.
What about iris?
Depends on the shape of the ROC, so it's always a bit of an educated guess, but I would say that iris will be similar, maybe a little bit better. But you only have 2.
Yeah, that's yes, that's the question. As for we worked a bit on template production as well, but we were focusing mainly, on this classical stuff like fuzzy commitment, fuzzy vault, and I don't see any more papers on that. I guess that they've been fully exploited somehow, or do you think there is still room for improvements for those kind of protocols?
Well, they have the fundamental problem that they will not, that their performance is strongly related to the biometric performance, so they will never get better. If you can get very good biometrics, these things are useful. So it may work for iris, it may work for finger vein if you can really get those low error rates. But I think the whole stuff is a bit researched out.
So essentially you are saying that for template protection the future is more or less homomorphic encryption?
Not completely. Because homomorphic encryption always requires some kind of, where's my table? It always requires some kind of key management. So, but if you have a device like a smartphone, then that could do the key management for you securely inside in a secure element, and then this would work. But without something like that, it would be harder. So in combination with the smartphone, I think homomorphic encryption would be a more promising solution.